Yeah. So graphs. Let's first see what are graphs. Right. So basically, like informally, if you say a graph is just some collection of vertices or nodes, like they are just some points in space which are connected by a bunch of lines called edges. So like this is these are vertices, or you like they are sometimes also called nodes, and the connections between them are called edges. So wait a second. Yeah, so um wait a second. Hmm. Yeah. Wait a second. Okay. So graphs can be of many types. Like for example, you can even have like directed edges, which are just like edges which have directions to them. Like you can only go through them one way. Like you can only go from here to here, not uh, and not the other way around. Like you can only go from here to here and not the other way around. And the the point is, like you can classify graphs based on this. Like for example, you can even have multiple connections between the same pair of vertices or nodes. Like there can be a graph like uh, this. So this is called multigraph. Like and a graph which has no directionality to its edges. Like every edge
Man,
can.
man, can you move a little closer to the mic? Your voice is not clear.
Oh, okay. I don't know. Like I think I'm actually like pretty close already. Um, I don't know. Wait. Let me like try. Now is it a bit better, or is it still the same?
Yeah, that's cool, I think.
Yeah, yeah. Okay. It's now better, right? Okay. So yeah. So this is a multi-graph, and a graph which has no directionality to its edges is called an undirected graph, and a graph which does have directionality to its edges is called a directed graph. For example, this this one is a directed graph. So yeah. So that's about the types of graphs. And yeah, a graph which has only at most one edge between a pair of vertices, for example, like which is not a multi-graph, is called a simple graph. So for example, like the types of graphs you will deal with most are simple undirected graph. So for example, this like something like this would be a simple undirected graph, like or like basically anything at all you can think about it. But for example, this is not a simple undirected graph because there are two edges between the same pair of vertices, so this is a multi-graph. Like this is not a simple graph, it's just it's it is an undirected graph because there is no directionality to the edges. But it is a multi-graph. So it's not an undirected simple graph. It is undirected, but it is not simple. So the types of graphs that you will deal with most in competitive programming are undirected simple graphs. Like most of the problems ask you to do something about like solve some problem on those graphs. Okay, so um, Now that's about the types of graphs. Now let's see how do we represent these graphs in our actual code. So mainly there are three different types of representations that you have. One of the first one is the adjacency list. Like this is also the one that is the most used by people. So for example, for this graph, I'll just number the vertices. 0, 1, 2, 3, 4, and let's connect to input. Okay. So for this view, basically just for you, for each vertex you store which vertex it is adjacent to. For example, like which edge, which vertex it is connected to by an edge. So for example, 0 is connected to 1 and 2 by an edge. So for 0 you would store 1 and 2. For 1 it is connected to 0 and 4 by an edge. So you, for 1 you would store 0 and 4. For 2 you would store 0 and 3, 0, 3 and 4, because it is also connected to 4. And for 3 you would store uh, 2, 4, and for 4 you would store uh, 1, 2 and 3. Yeah, so those are basically like that is basically the adjacency list representation. Like for every vertex in your graph you store a list of the vertices it is adjacent to. In a graph you would like in C++ you would use this using a vector of vectors. So like you would do something like vector vector int uh, and something like this. And then whenever you have an edge, like in the input, whenever you have an edge u comma v, so you will just do g of u dot push back v, and you will do g of v dot push back u. uh, yeah, so that's yeah, so that's basically the way you do it for adjacency list. Now the second common way is adjacency matrices. So basically an adjacency matrix, you just oh yeah, I forgot to mention that the last representation, since you only store for each vertex how many the amount of space that you take for each vertex is proportional to the number of vertices it is, like it is exactly equal to the number of vertices it is connected to. So the total space complexity of the adjacency list approach will be the sum of the degrees. Okay, wait, I shouldn't use the so it will be the sum of how many vertices each vertex is adjacent to, like the sum of this quantity over all vertices. And it is like for every single edge you will count it twice in this like basically every single edge is kind of stored twice in your list. For example, 0, 1 is stored as in the form of 0, like 1 being adjacent to 0. So like 1 is in 0's list and 0 is in 1's list, and it appears nowhere else. Like there is no other sign, there is no indication that this edge is there. Like basically whenever you get an edge u comma v, the only thing you do is you increase the sizes of two lists by 1. So this the total size of all the lists is going to be 2 times the number of edges. Like basically the thing that you did here, g of u dot push dash back v and g of v dot push dash back u. So the only thing you are doing here, for every single edge you are just increasing the size of two lists by 1 each. So that means that the at the end, the total size of all your lists is going to be two times the number of edges. So that is like so basically the space complexity of this is big O of n plus m, because you need to store n lists, and the total sizes of each of those, like the total sum of sizes of all those lists is big O of m. So the space complexity of this approach is O of n plus m, and the time complexity is O of m. Now let's go to adjacency matrix. So in adjacency matrix, what you do is that you store for every single pair of vertices, whether it is uh, whether it is adjacent to uh, other vertex or not. So basically, for every single pair of vertices, you store in a matrix whether they are connected. Matrix is basically just a grid. So like you store in a grid whether two vertices are adjacent or not. For example, let's say we have the same graph from last time. Okay, let me just add one more row. So the same graph from last time, represented in adjacency matrix form, would be, so basically for uh, every two, like for example this is the cell 0 comma 0, so 0 is not connected to 0 because like 0 does not have an edge to itself. Like of course it could have, there is no such rule stating that you cannot have an edge from 0 to itself or any vertex to itself, but say in this case you do not have an edge from that vertex to itself. So so for everything on the diagonal you'll just write 0 by default, and for 0 and 1 they are connected, so yes you will write 1, and for 1 and 0 they are also connected, so you'll write 1 as well. For 2 and 0 they are connected, yes, so we'll write 1 there as well. 0 and 2, as a consequence, they are also connected. 0 and 3 are not connected, so we'll write a 0 there. And yeah, like you can fill this in a similar way. Let me just fill it out. 1 and 3 is also not connected. 2 and 3 are connected. 1 and 4 are connected. uh, 2 and 4 are connected, yes. 4 and 3 are connected. So this is basically the adjacency matrix representation. Now the thing is that in this you store every single piece of information about which edge is present, and more importantly also about which edge is not present. So the thing is you are storing a lot of redundant information over here, but sometimes it can be convenient also, the adjacency matrix representation, which is why it is sometimes we use it in, like it sometimes makes more sense to use it instead of the adjacency list representation. So but this is going to have O of n square space, because you are storing for all the pairs of vertices whether they are connected to each other or not. So this is going to be O of n square space, and obviously time complexity is just going to be O of m. uh, right, and the third major way is edge list representation. So basically in this you just store, as the name suggests, you store a list of edges. For example, let's just take our the graph from last time, right? So this is our graph again. So in this you'll just store the list 0 1 1 4 0 2 2 3 3 4 uh 2 4 and Yeah, okay, that's all. So yeah, that's all the three representations. So now let's talk about some definitions in a graph. What does it mean for two vertices to be connected to each other? So for example, if we see in this graph, okay, and yeah, okay, one more important thing. So how do you uh, so how do you extend the above definitions, like how do you extend the above ways of representation for directed graphs, right? We only viewed undirected graphs here. So for example, for it's very simple, you just need to add a little bit of so for example, for the adjacency list representation, you can just whenever you receive an edge u to v, like it is directed from u towards v, so you can just do only g of u dot push dash back v, and you can like omit the second part, which is g of v dot push dash back u, because in this case it is not necessary that v is also connected to u by an edge. It only I mean, sorry, u is also connected to v by an edge. It's you are only given the information that v is connected to u by an edge. So yeah, like there is an edge from u to v. It is not guaranteed that there is an edge from v to u as well, which was true in the above case. And in the adjacency matrix representation as well, the only thing that you need to change is just once again, you, instead of having both m of uv equals m of vu equals 1, you just do m of uv equals 1, and that's all. Like because once again, like the previous case, you don't have the guarantee that there will be an edge from v to u as well. Uh, if there is an edge from u to v. Okay, so the next thing is edge list, and edge list is also very simple. Like in the above case, you by default assume that every edge was undirected, but now you will just assume by default that every edge is directed, and whenever you receive some edge which is pointing two ways, then you can just add it both times. For example, you have something like this, like there is something u to v as well, and you have something from v to u as well. So in this case, you can just add both the pairs u comma v and v comma u to your edge list, and yeah, you'll be done. So okay, what's next? Yeah, so um, connectedness of two vertices. So the connectedness is defined as whether you can reach a vertex from another vertex. For example, uh, like in this graph, once again, let's just take that one. Yeah, uh, 0. Okay, so in this, every vertex is reachable from every other vertex. You can check that uh, every vertex is reachable from every other vertex. That means that every pair of vertices are connected. Like every single pair of vertices is connected to each other. For example, 0, you can reach 4 from 0 by this path or this path. Like you can take any of those two paths anyway. So yeah, and for example, for this graph, and the uh, and for example, for this graph, like you have something like this. So for this graph, you can't reach this vertex from this one. So these two vertices are not connected to each other. Like connectedness does not only mean that the two vertices are directly connected by an edge. It means that the two vertices are reachable from each other. Like in an undirected graph, it means that the two vertices are reachable from one another, and a graph in which every pair of vertices is connected is known as a connected graph. Like you can reach every pair of vertices from each other, like you can reach from u to v for every u and v. So for example, this is a connected graph, and if you think about this as one big graph, then this is not connected because there are like two parts of this graph. And now the thing is, these parts are called connected components. So like this graph has a connected graph, obviously has only one connected component, which is itself. But a non-connected graph has two or more connected components. For example, this graph has this connected component and this connected component. So yeah, so now we'll learn how to find connected components. So uh, the point is that like in order to find connected components, you basically uh, let's try to solve a simpler problem. Like for given any vertex u, let's try to mark every single vertex that is reachable from you by using some sequence of edges, right? So if you are given a graph, and let's try to solve a simpler problem on that graph, which is to find every single vertex that can be reached from you by some sequence of edges. And obviously that's going to be its connected component, right? Because it's like every single vertex in that component is reachable from each other, because like for example v and w. So v you can reach from u, that is the original like premise that we assumed. W you can also reach from u. So that means that since every edge is undirected, so you can reach u from v as well. So you can go from v to u, and then you can go from u to w. So v and w are also connected to each other. So if v and u are connected and u and w are connected, then v and w are also connected to each other. So yeah, that is the first thing that you can observe. So basically this is what tells you that solving this reduced problem, by solving this reduced problem you can solve our original problem as well, which was to find all connected components in a graph. So yeah, so basically from you, let's think about the vertices adjacent to you, right? Like you want to mark every single vertex which is reachable from you by using some sequence of edges. So let's think about every vertex which is reachable from you. Like surely you need to mark at least those vertices, right? Because these are the ones which are reachable by exactly one edge. So obviously you do need to mark at least those edges. So uh, I mean you do need to mark at least those vertices. So you'll mark them, and now what? So now you need to call, like let's say this function is like okay, let's just name it what it is. Let's say this function dfs of u. Let's say you have this magical function which can, like when you give it you can it marks every vertex that is reachable from u by some sequence of edges, and it gives like gives those marks vertices back to you. So we don't know how this works, but it does work somehow. So dfs of u, right? So now everything adjacent to it. Now let's call dfs on those as well, because if it's reachable from, like if it is to be reachable from you, then there are only two possibilities. It will either take exactly one edge to reach from you, so in that case we have already marked it because we have marked everything adjacent to you, and or the second case is that it will take two or more edges. So in that case the starting point must be one of these vertices only, because there is no other starting point that you can think about. Like if you think about the path from you to that vertex, if you think about the second vertex on that path, then that must be one of the vertices you just marked. So for every vertex here you also call DFS, for every vertex V here you also call DFS of V. Right. So for every single adjacent vertex, so first DFS of U, what it does, it marks you, uh, and then for every uh, V adjacent to you, it calls DFS of V as well. But the problem, like, this is the first thought that you might have, but the problem is that this algorithm works fine for um, graphs, basically, like you also but the problem is, like, this algorithm seems to work fine for like the first layer, but then once you get to the second layer, you just get back here, because obviously if u is adjacent to v, then v is also adjacent to u. So you'll just come back to u again, and then you'll go back to v, and then you'll come back to u, and you'll get stuck in an infinite loop. So in order to avoid this, what you can, like, there's a very simple fix. What you can do is that if you have already marked for every v adjacent to you, if it has not already been marked, like the condition is that if it has not already been marked, then you will call DFS on that. Otherwise you'll just let it go. Like, you have already explored everything from that vertex, so it's fine if you let that go, right? So if it has not already been marked, uh, then you should call DFS of V. Otherwise you should just let it go, because everything that could have been explored from it has already been explored. So um, yeah, so basically let's just see a visualization of this algorithm. uh, right. So yeah, let's say we start from this vertex. So initially, okay, DFS part, okay. So did you get that the DFS function is basically, what we are trying to do in the DFS function is basically just mark every vertex adjacent to basically mark every vertex that is reachable from you by some sequence of edges. Like, do you get that? That is what we are trying to do. Yeah. So the point is that now there are two cases. For a vertex to be reachable from you, it either needs to be adjacent to you, or it needs to be it will be reachable from one of your adjacent vertices. Do you get this part? Like, basically it will be adjacent to you itself, or it will be adjacent to someone who is it will be reachable from someone who is adjacent to you. There are no other cases. Like, either you are a neighbor of you, or you are reachable from a neighbor of you, because otherwise, see, what will happen is that if some vertex v is reachable from you, but it is neither a neighbor of, it is not a neighbor of you, then you can consider the path from you to that vertex, and it will have at least 3 nodes, right? Because it is not a neighbor, so it cannot have 2 nodes. So it will have at least 3 nodes, and you can just consider the second node on that path. So that's going to be a neighbor of you, and it must be reachable from that neighbor. So yes, so yeah, that's it must be reachable from that neighbor. So now for every yeah, exactly. No, like, adjacent to you, or it is reachable from someone adjacent to you. Like for example, on this graph, either for every vertex, for example this vertex, it is not adjacent to you, but it is reachable from someone adjacent to you. Like this vertex is adjacent to you and it is reachable from that vertex. So if someone is reachable from you, basically, so like if this is reachable from you, right, so this path, you take the second vertex here, or this is maybe a bad example, let's take this vertex. So on this vertex is reachable from you, and if you take the second vertex on that path, it will also be reachable from there as well, because like this path is there for it to reach. You get that, right? Like if it will either be reachable from you or it will be reachable from a neighbor of you. Like yeah, so now our algorithm is based on that only. So you will first, like you will check every adjacent vertex. If it has already been marked, so you have explored everything that you could from there, so there is no point exploring that further. But now you need to explore for the ones that have not been marked. You need to mark them and then you need to explore further, like where can you get from there. So that's why we call DFS of V only if it has not already been marked, because otherwise we will get stuck in an infinite loop. So yeah, so if it hasn't been already marked, then only you will call DFS of V, otherwise you'll get stuck in an infinite loop. And yeah, that's basically it. So you your DFS function just consists of marking you, and for every V adjacent to you, if it is not already been marked, then you will call DFS of V. Okay, now you got it, right? Yeah. Okay. Fine. So yeah, so the next yeah, so now how can this be used to find connected components? Well, just go in yeah, so I was trying to like visualize DFS right now. So yeah, so let's start from this vertex. So now first from this vertex, these two vertices are adjacent to it, but let's say you decide to explore this vertex first. Now you now from this vertex is also adjacent to it, but since it has already been marked, like you have already been done with it, so you won't mark it again. So you'll go on to the next, you'll mark this first and then you'll go on to the other vertices that are yet to be marked. So now you'll mark this vertex, and now the next vertex which is adjacent to it, you'll mark this one. Now the next vertex which is adjacent to this one, you'll mark this one, and now the next vertex which is adjacent to this one, you'll mark this one. So you first visited this, then you visited this, then you visited this, then you visited this, then you visited this, and then this. So basically you are exploring as far deep as you can uh, before breaking and moving back. So that's why this algorithm is called depth first search. Basically you are like searching as much till as much depth as you can, and then you are returning back once you can't search any deeper. uh, and yeah, that's depth first search, which is DFS for short. Okay, so now I want to cover a few applications of DFS, but before that, yeah, so let's look at how it can be used to solve the connected components problem. So let's say you want to find the number of connected components of a graph, right? So how do you do that? So you just go through the vertices in any order, and for example, if you have vertices numbered 1, 2, and so on till n, then you can just go through them in this order. So you'll first, like for every vertex v from 1 to n. If v has not already been marked, then you'll call dfs of v and mark everything that is reachable from v by some sequence of edges. If v not marked, then you'll call dfs of v and you'll increment the number of connected components, because like you just found a new one which is not reachable from any other component so far. For example, for this graph, right, let's say it's just two triangles. This is our graph, right? This box is not part of the graph. Only these two triangles are part of the graph. So obviously this has two connected components. Let's see how many our algorithm gives us. So first, let's just number the vertices: 1 2 3 4 5. Okay, let's see, 6. Okay. So you'll start from 1, then you'll go to 2, and now 2 is adjacent to 6. Now you'll go to 6, and now you're done. Basically everything you could explore from this one vertex is now been explored. And now you go to 2. 2 is already marked, so you won't explore that vertex again. Now you go to 3. So now 3 is uh, not marked yet, so you'll call dfs of 3. So dfs of 3, then now you call dfs of 4, then from 4 you call dfs of 5, and yeah, everything has been explored. So here initially the connected components value is 0. Now after this component it becomes 1, and after this component it becomes 2, and 2 is indeed the number of connected components we have in this graph. So um, yeah, and important to note that the DFS algorithm is O of n plus m, where n is the number of vertices and m is the number of edges. Okay. So because of the fact that you will only visit every vertex at most once, because you are not going to visit any vertex which has already been visited before. So because of that fact, you'll only visit every vertex at most once, and from every vertex you are going to try to explore every edge at most once. So that and for every edge you are going to try to explore it at most twice, one from each end. Like you'll try to explore it once from this end, and you'll try to explore it once from this end. Of course one of these will be unsuccessful because the other one has already gotten to that. Like you'll remember that, oh, I have already gone through this edge before, and it will be like one of these will be useless, or even two of them can also be useless, because if you have like this edge is like never even explored. So that can be a possibility as well. But yeah, the point is that every edge you will go through a maximum of 2 times. Like of course it's going to be less than that in a lot of cases, but you will go through every edge a maximum of 2 times, like once from this end and once from this end, because you are only going to explore every vertex at most once because of the marked not exploring marked vertices again thing. So this is big O of n plus m. Yeah. So okay. So let's do the CSES problem on this. Like basically, what you can do is you can, yeah. So building roads. This problem is about connected components. So basically, byteland has n cities and m roads between them. The goal is to construct. Oh, m is the number of edges. Um, m is the number of edges in the graph. Like you'll only explore every edge at most twice. You'll explore it one time from both ends. So yeah. Uh, all right. So yeah. So let's try to like do this CSES problem. Uh, Byteland has n cities and m roads between them. The goal is to construct new roads so that there is a route between any two cities. Your task is to find out the minimum number of roads required and also determine which roads should be built. Um, so yeah, let's just uh, like basically the point is that for example, okay, I'll just take this example. So um, yeah, so for example, for this graph, what do you think is going to be the answer? Okay, should I put the link in the chat? Um, no, like for this graph, it's going to be like you need to find out the number of roads to be that you need to build. Yeah, you need to have at most one like you need to have at least one edge, because if you don't build any new roads, then it's not going to be possible to connect everything. So yeah, so let's say you build this road. So basically, for example, if you take this thing, uh, right, let's say you take this graph, uh, like three connected components, then what do you think is going to be the answer is in this case? uh yeah, um from each city they just need to be connected, like basically you should be able to get from every city to every other city. It's not necessary that the path should be unique. Yeah, so basically you need to like for if you add one edge, you can connect any two components, right? So like for example, by adding this edge, okay, wait. Yeah, for example, yeah, for example, by adding this edge, I can connect these two components, but this one is still left. So by adding one edge, I can connect at most two components. So that means that in order to connect all of the components, like in order to connect all of these components into one big component, I need at least number of component minus one edges, because each edge can only connect two components, and like you need to have every component connected by an edge to some other component at least once, so that and all of them should be connected as well. So yeah, it's pretty easy to see that you need uh, at least number of components minus one edges in order to, yeah, there should be only one connected component when you are done with everything. So like the point is that any step you perform can reduce the number of connected components by a maximum of one. uh, so you will need at least number of connected components minus one operations in order to reduce it to one big connected component. So does anyone have any doubt till now in this? Okay. Um. So yeah. I hope nobody had any doubt in this. So yeah, let's once go through the code for this. So basically, um, in order to find the connected components. um, okay, so first let's just input, and I do recommend trying to code these up yourself after the lecture as well, because um, yeah, it is important to code them yourself as well instead of just watching someone code them. Yeah, so basically, this is the adjacency list representation of a graph. Basically, for every edge u comma v that I get in input, I am going to be adding v to u's list and adding u to v's list. And now, okay, uh, let's just, okay, I normally use lambdas for this part, but I think you guys don't know lambdas probably, so I will just use normal global variables for that part. Yeah, so basically, uh, we used this adjacency list of size 100,000 because n is at most 100,000 in this case. So yeah, and so for every let's try to okay, so let's try the dfs function. uh, uh, and this is the visited vector, like the marked vector that I talked about. What is this? Okay, and for you, basically you need to, for every vertex in the adjacency list of this, if it is not already marked, okay, so first off you need to mark v itself, of course, and second of all, then you need to, if the vertex is not visited yet, then you need to visit it. And also we'll keep a vector of vectors called components, which is just basically everything, like the connected components that we have found till now. So we will just components dot back dot push back v. Basically, the latest component will add v to that. uh, Basically, for example, if we have the connected components till now, we have 145, uh, like the current connected component till now is 145, and I want to add 6 to that. So I should just like uh, or for example, 6 is not connected in my in the current component. So in that case, I need to finish the 1451 for now, and then make a new one for 6. um, and yeah, if 6 was connected, then we do this, like we the latest component vector, this is just comps dot back, like the latest vector which is in components, like the rightmost vector, like the one that we just added just now, and dot push dash back v, like basically we add v to that. And yeah, now go from 1 to n in any order. If v has I has not been visited, then dfs from there. And also, yeah, components dot emplace back. Emplace back is a useful function which basically just means that you are adding an empty vector to the components vector, like to the back of your components vector you are adding the empty vector. And yeah, components dot emplace back and dfs I. Now components dot size represents the number of components that there are. So we need, as we discussed earlier, we need at most at least components dot size minus one operations to like get the edges to like get the entire city to be connected, right? to get the entire graph to be connected, because in every operation you can only merge at most two components into one component. Basically you are decreasing the number of components by a maximum of one. So yeah, that's basically it. So now for like basically you'll connect all the first vertices in all of the components you have into one big chain. For example, like if I will see here, then let's say you have three like this. Okay. um, these are your components and these are the first vertices in all your components. Then you'll just connect them by lines, right? This and this. Okay. So yeah, that's it. uh so basically you just connect the first vertices of every single component into one big chain. So components dot size minus one I plus uh, components of I0 plus 1, because you need one index. We first converted to 0 index and now we are converting back to one index. And components of this, yeah. um and that's basically it. uh, okay, let's try to submit. Okay. Just let me alright. uh, I hope you have. I think what is it? Okay. uh, did I name it? Yes, yes, city. See. Yeah, okay. Apparently it seems that I made a mistake. What did I do? Oh, okay, okay, okay. Never mind. Okay, so I just made a really bad mistake, which is I forgot. Like I basically connected the first vertex of every component with the second one of every component. Not uh, okay. Uh, yeah. So basically, let's see is yeah. Okay. Okay. Uh, do you get the finding components part? Yeah, we are connecting first city of one component to the first city of the next component. Yeah. So what part do you not get in that uh, in this code? What part do you not understand here? Like, is this part fine, or do you have a problem with this part? Okay, this one, right? Okay. So basically, the first line is basically just saying that in the most recent component we are adding wheat, to our most recent component. Like in our most recent component, we are adding v, and the second line basically just says that we are marking v, like we have already we are marking v as visited, and the next line just says that for every u which is adjacent to v, if u has not already been visited, then you'll call dfs on u as well. uh, yeah, that's basically it. So uh, uh, do you get that, or do you still have a problem with some specific line here? Okay. Okay. Fine. So yeah. And you guys should try to implement this yourself as well, um, after the lecture. So yeah. Anyway, I was thinking that I would discuss. Uh, no, like when you call DFS, when you call DFS for a node, basically recursively it marks every single node that is reachable from it. So basically, the point is that, but you don't know when you are at a certain node what nodes are reachable from it. You only know the next node, right? Is that clear? So basically, you need to explore all those nodes and then all the nodes adjacent to them as well, and then all the nodes adjacent to them as well, and so on. So you need to you need to go through this entire chain of adjacencies, and then you need to like in this case, the reason we are calling it for all nodes is different. Basically, when you have only one component, then it's fine, but this only marks dfs only marks the vertices which are in the component of the current vertex, not every single vertex. So that's why you need to call it for every node, so to make sure that you count every single connected component that you have in the graph. Now is it clear? Okay. um, like basically important thing is that dfs marks every single vertex that is reachable from the current vertex, not just directly adjacent, but everything that is reachable from the current vertex. Like this is very important. Just don't forget it. It marks everything that is in the connected component of this vertex, not just the vertices that are directly reachable from it by one edge. It marks vertices which are reachable from it by two edges, three edges, any number of edges. Okay. So yeah, now I was thinking that we would do some applications of DFS, but since the time is less, I will now cover DFS. So basically, the way I like to think about DFS is that, for example, in DFS, the yeah, we are going to do shortest path as well, but after BFS. Okay. Yeah. So um, in DFS, basically the most recent node that you explored, right? The ones that the vertices that are adjacent to that get explored the first. For example, uh, in this thing, uh, like you immediately explore every single thing that you have access to explore. Basically this you explore, then you explore, like basically mark this, then this, then this, then this, then this, then this, and so on. But in bfs the important distinction is that you will uh, you will visit nodes sequentially, like step by step. Like you won't go um, like very like you won't go very deep initially, you will go equally deep everywhere. So basically what I'm trying to say is that you'll first go here and then you'll go here. Now you won't explore this one, first you'll explore this one, then this one, then this one, and then you'll explore this. Now, even from here as well, you won't explore this next vertex. You'll first explore this one, then this one, then this one, and then at the end you'll explore this one. So basically, the special thing about BFS is that it always explores vertices in sorted order of distance from the source vertex. So basically, there is this source vertex which you are calling BFS from, and based on the order of distance from that vertex, you first visit vertices which are closer to the source, and then you visit vertices which are farther from the source. And this is true regardless of what vertices you consider. So for example, for DFS, so this is DFS, let's just number what order we explode them in, right? 0 1 2 3 4 5 6 7 8 9. um, 0 1 2 3 4 5 6 7 8 9. Okay. So you can see the difference, right? This all the vertices at distance 1 got explored first, then all the vertices at distance 2, then there was just one vertex at distance 3 and it got explored at the end. And in this case, you first explored this branch, then you explored this branch, and then you explored this branch, and then you explode this branch. So you go branch by branch, and in this you go level by level. Like you explore this level first, then you go this level, then you go this level, and so on. So basically there is only one tiny little change that you need to make to DFS. So like the way you can think about it is that DFS is like impatient. It wants to immediately explore every node that it can explore, while BFS is like a patient algorithm. Like you can like it waits before for example, once you visited one, uh, it doesn't like immediately want to explore 5. It will say, okay, I discovered 2 3 4 first, like 2 3 4 are indeed like more deserving of my attention currently than 5, so I'll first explore 2 3 4 and then I'll explore 5. So basically the way you can think about this is that DFS is like an impatient algorithm that you need to like it needs to explore every vertex the moment it can explore it. And for BFS it's a patient algorithm, like it will take its time before exploring any vertex. So yeah, that's the thing, like it will explore every vertex at a certain time, like and DFS will just explore every vertex whenever it is available. So the thing is DFS okay, so it is like normally DFS uses a stack while BFS uses a queue. So do you guys know what a stack and a queue means? Like what the principle of stack is and what the principle of a queue is? Yeah, yeah. So the principle of a stack is just like last like you go, yeah, basically LIFO, basically the last thing that went into it, like a stack of papers, you place something on the top, then the next time you came back to that stack, the first one you pick up will be the last one you put down. And the queue is like you first in first out, like you are the one that the thing that came in first will go out first. So DFS is a stack based algorithm. Basically, the thing that last went in is the first to come out. So basically, in your stack of vertices, initially you have 0, then you have 1. Now 4, 6, 8 are also in your stack, but they are they have been added first. So now you need to explore. So basically, like, the point is that DFS works like stack. So it is a LIFO algorithm. Like, the thing that you the thing that goes in last comes out first. Like, 4 by rights should be after 1, but it's sadly not like it. 2 comes after 1, and then 3 comes after 2, and then it is 4's turn. So basically, this works on the principle of stack. Like, you put the stack of 4, but before you could take it off, you put the stack of 2. So you took off the stack of 2, and then before you could take off the stack of 4, you again put the stack of 3, and then you took it off, and then you like basically you then you popped off 4 from your stack, and then you went to 5, and so on. So basically, this is a LIFO algorithm, and BFS is a FIFO algorithm. Like, when the first thing that goes in comes out first. So for example, 1 went in first. Okay, 1 is like, anyway, we're going in first. 1, 2, 3, 4, you pushed everything in that to your stack, I mean, sorry, queue, and then you popped 1 from your queue, and now the next one will not be 5 like DFS, it will be 2, because yeah. So basically, the next one will not be this vertex, it will be this vertex, because the principle of queue is that the vertex which arrived here first has the first rights to uh, be popped from the queue. So basically, the vertex which arrived here first gets popped first from the queue. So this okay rather than basically, the point is that you can use this to explore level by level, and more importantly, you can use this to find out the distances from a vertex to any other vertex. Can you see how we can do that? Like, do you understand how we can do that uh, just using the BFS algorithm? Yeah, exactly. Like, you count the number of levels you passed in order to arrive at that vertex. Like, you, for example, you passed 2 levels. Like, this is level 0, this is level 1, this entire thing, and this is level 2. So basically, you just count the number of levels that you went through in order to arrive at that vertex, and the path BFS follows in order to explore a certain vertex will always be the shortest possible one. So basically, what you can do is that you can maintain a queue. Okay, like, we'll cover this code as well, so no need to worry. So we'll maintain a queue, and while queue is not empty, we will let v equals the top thing in the queue, and okay, it's actually not top, it's actually like front. Like, basically, in a stack you use dot front, I mean, in a stack you use dot top, and in a queue you use dot front in order to access the last element. Like, it makes sense as well, right? A queue, in a queue, in order to refer to the first person, you use the word front, and in a stack, in order to refer to the front of the stack, you use the word top, because it's like top to bottom. Like, the first thing you take from a stack is going to be the top thing. So it makes sense as well. So v is q dot front, and for every vertex uh, you adjacent to v, and you also need to take care, like DFS, you also need to take care of vertices are marked or not. So for you adjacent to v, if u is not marked. Okay, and mark v, of course. First of all, mark v. If u is not marked, then in our queue we will add u. Like basically whenever its turn is there, it will come out of the queue, and then you will explore that vertex and all its neighbors. uh, and in order to find the distance, you can just maintain vector d of size n, and initially the distance of source is obviously the distance of the source is obviously 0, and for if u is not marked, then d of u is equal to d of v plus 1, because this is the first time you are exploring, and since you are fully exploring every single level before moving to the next level, you know that this is going to be the first time that you ever find you by moving this many levels, and you can't find you by moving this many less than this many levels, because if there was a way to find you by moving less than this many levels, then you would have found it before, because bfs fully explores every single level before moving to the next level. So does that make sense? Yeah, yeah, we are inserting source to queue. Sorry, I forgot about that. Yeah, you we are inserting source to queue. Yeah. uh, any other doubt? Okay. um, Great. Okay. So yeah, so let's do a CSES problem based on this, right? Uh, let's do the CSES problem based on this. uh, okay. Message route. Yes. Okay. So basically you need to find the distance between the vertex 1 and n in this. uh, um Probably not, because we like it's already been a lot of time, and I also need to discuss shortest paths. So probably not, but I will give some harder problems in the homework. Yeah. Uh, okay. So um, yeah. So basically, you need to find the distance between the vertices 1 and n, like the shortest possible path. And you also need to print an example of such a route. So can you think of a way how to print an example of such a route? Like how can you find such a route? Finding the distance is fine, but how can you think of how you can find such a route after finding the length of this route? Like in this case, you don't only need to find. Yeah. I mean, okay. If you have already studied it, then um, please give some chance to others as well to like think. Okay, so like those who have not done it, like think for 2 minutes and uh, think about how you can find. Yeah. No, not one element exactly. uh, like we keep like you are on the right track, but only one element will not work, because for example from for example, let's say from this level, if we um, from this level, if we uh, keep track of this element only, then you don't know whether this vertex is going from this path or it is going from this path. So at every level, um, no, for like parent arrays, like basically you can store a parent array for anything, and this is basically a type of tree only. It's known as the BFS tree, but yeah, that is out of scope for this lecture. But basically, the point is that you can like you are on the right track basically. So the point is that you can like for each vertex, whoever marked it, like if for you adjacent to V, this thing that we have here. So whoever marked it, like for every vertex, you will store who was the vertex that marked it. So for u adjacent to V, we will, if u is not marked, then q dot push u d of u equals d of v plus 1, and we will also add one other thing, which is parent of v is equal to u. This parent is called the parent array, as Advait was saying. So this is the parent array, and basically what it does is that it tells you the complete information about the path from this current node to the source. Basically, for if you had done this for this one, then you would have gotten that the uh, no, there are not two parents. There is only one parent, because see here, you will only explore every vertex exactly once, because like once it's been marked, then you will okay. Yeah. So basically, once it has already been marked, then you will not like mark it again. Wait, wait. Yeah, so you won't mark it again. Yeah, so that's the oh my god, okay, why does this keep scrolling? Yeah, I will implement this as well. So yeah, so basically this gives you the parent array gives you the complete information about the path from this node to the source. And using the parent array, you can just keep going up until you go to the source, and at that point you have found the entire path. Okay, so now let's see the implementation for this. Right. Um, Basically, uh, the main part I think is a problem. Okay. uh, yeah, if the graph has a cycle, this would still work, because you only set the parent every time you get it to, like you only set the parent when you get to it the first time. Like you won't visit any vertex twice, like you won't mark any vertex twice, because the first time you marked it, after the first time you marked it, whenever you reach it, you'll see that okay, this is already been marked, so I don't need to mark it again. Like, does that make sense? Like if it has a cycle, you will just ignore the two ways of reaching it. You will just pretend like for you there is just one way of reaching any vertex, because once a vertex has been marked, it can't be marked again. So every parent would be unique, like the parent of every vertex would be unique, and will be the next vertex on the shortest path from this vertex to the source. Like do you get that? Okay. um, so this is the efficiency list part. And now we use the and yeah, uh, will set all the other distances to some really large value except the source distance, because initially we don't know what is the distance, so we need to set it to some really large value in order to detect whenever the vertex is not reachable, because you also need to print if there are no roots, then you need to print impossible. So yeah, so we'll first we go into the queue, and while queue is not empty, and yeah, you will also d of 2 equals 0, because uh, the source is, yeah, q dot front, and q dot pop for v3 if the we are not in, and also um, um, q d, okay, and also get a few questions, right, and this is also equals to, um, yeah, uh, and you also need to store the parent array, and initially for every vertex the parent is going to be -1, and for the source it is anyway always going to be -1, because there is no one above the source, right? 0 is our source and there is no one above that, because like you get what I mean, right? So yeah, p of u is now v, um, and yeah, now if the d of n minus 1 is m, like m is some really large value that capital M is some really large value I said above, so then it's impossible to reach, and otherwise it is possible. Okay, am I supposed to print possible or not? Okay, I am not supposed to print possible, so I'll just print d of d of n minus 1. Okay, it's the minimum number of computers on such a valid root. So in this case, we started from 0. So okay, we should be starting from 1, because it's we are counting the number of edges ordinarily. Like d of 0 is 0 because you need to travel 0 edges to get from 0 to 0. But you need to travel one vertex to travel from 0 to 0. Uh, right, so that's the point, and now while p of n minus 1, while okay, so uh, current is path, current is n minus 1, while p of current is not uh, while current is not minus 1, path dot push back current, and current equals parent of current. Yeah, that's basically it, and now print the paths, and then print any value solution. Okay, and yeah, you also need to reverse the path, because you are currently, the path you found is 1 from n to 1, but you need to find 1 from 1 to n. So yeah, the path of I, uh, um, yeah. Okay, let me submit. Okay, what did I do wrong here? Oh, okay, I forgot to plus. Okay. because it was one index instead of zero index. Uh, so so yeah, this is the implementation for it. Basically, this is the main part is this one. Um, yeah, wait. Okay, I'll just use this. Um, okay. Uh, wait, and also if you have a problem in something, then you can just ask me right now. No, no. I okay. I'll share on both. It's fine. Copy. Okay. 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 Indeed. By mistake too. Okay. Fine. Uh, the next thing we are so does anyone have any problem with this BFS thing? Like the main part is this like and yeah. So the important part is that you can use the parents array to restore this, and BFS explores everything layer by layer, and yeah, that's basically the important stuff about it. Okay. So yeah. Uh, the next thing is Dijkstra. So I think we won't have time to maybe we won't have time to implement that because I was planning to have this of 2 hours. Um, yeah, uh, but I guess you guys can try to implement it yourself as a homework. So yeah, Dijkstra is basically in BFS we can find the shortest path from a source to any other vertex, but we can only do that in an unweighted graph where the edges do not have weights. But in Dijkstra we can do that for any graph where all the edges have positive weights. So basically this for example, this has weight 4, this has weight 6, this has weight 5, this has weight, let's say I don't know, 7, this has weight 8, and I want to, let's say, um, get from this vertex to every other vertex. So what's going to be the shortest distance for me to do it? So for this vertex it's going to be um, 4. For this vertex you could either take the 4 plus 6 route, but it's going to be 10, which is uh, more costly than just directly going here with 7. So this is going to be 7, and this is going to be, you can either take this route or you could take this route, but you can check that the shortest possible route is 4 and 5, which is 9. So this is the shortest, and of course this is 0. Yeah, so this is basically all the um, distances, all the shortest distances from this vertex to this ticked vertex to every other vertex. So now the point is that you can use Dijkstra to solve the problem of this type. So, what is Dijkstra? It is just basically it is basically BFS only. In BFS, what you did, you explode level by level. So in this also you do a similar thing. At each step, at each step, um, So what you can view BFS as doing is that you can view BFS as that it is choosing the vertex with the least distance from the source at each step, and it is updating every vertex adjacent to it with the new distance based on that vertex's perception of everything. So for example, uh, initially, and Dijkstra is also doing the same thing. Basically, at each step, you will kind of choose the vertex. So, like, this is not different from BFS at all. The point is that at each step, you choose the vertex which least uh, distance from the source, and update everything. Oh my god, okay, my stylus is not working. Okay, choose the vertex with the least distance from the source. Okay, uh, and update everything. Adjacent to it. So basically, let's see how this would look like on this sort of graph. So on this graph, first of all, you only have the source. Uh, so and everything else is at infinite distance. So initially everything is at infinite distance, right? And now from the source is initially at zero distance. Uh, no, not exactly. It's not exactly BFS. Like, I'm just trying to make an analogy to BFS. So in BFS, what you do is that you just choose the front vertex, like the most recent vertex at every moment. Here, you don't choose the most recent vertex at every moment. You will choose the vertex which has been discovered. I mean, you will choose the vertex which has the least distance currently. In BFS, actually, the thing was that due to the unweightedness of the graph, the most recently discovered vertex was automatically the one with the least distance from the source. But in this, because of the weights, it is yeah, you could say that it is also like greedy, and it is also kind of like DP as well, because you are like iteratively updating the distances from the source. So I would say it's not like anything completely at all, like purely a greedy approach or purely a DP approach or anything. It's just something kind of different. Yeah, so basically everything is initialized, everything else is initially at infinite distance, and now you will go from the source to the adjacent vertex. So this is at distance 4, this is at distance 7, and yeah, like this is now going to be at distance 4 according to this edge. So 0, and now since 4 is less than infinity, like that's obvious. So since 4 is less than infinity, so you'll update this to 4, and since 7 is also less than infinity, so you'll update this to 7. Now you'll choose the one with the least distance from the source, which is this vertex currently 4, and you'll update the vertex adjacent to it, uh, which is just this one and this one. But 4 plus 6 is more than 7, so you won't be updating this, because the new distance that you get, 4 plus 6, is more than the current distance that you have. So the you have already found a better solution, so you will reject this one. So you won't put a new value for 7 here in your data structure. You'll just let 7 be for now, let this vertex be for now, and for this one it is initially at infinity, and now it is at now 4 plus 5 is 9. So, and since 9 is less than infinity, you will now you will now update the value of distance for this vertex to 9, and you will push it into your data structure. Now you will remove these two forever, like, and the important part about Dijkstra is that once a vertex is removed, it stays removed. Like, once you remove a vertex from your data structure, it never comes back again. Basically, the point is that you never come back to a vertex to revisit your decisions. Your initial decision is always correct about any given vertex. For example, once I pop 4 from my can we do the same thing for longest? For longest paths, the thing is, like, you can have arbitrarily big cycles, right? So um, you actually, like, longest paths does not usually exist in a uh, but yeah, in a graph where everything has negative weights, it's, yeah, if there's a cycle, the longest path is infinite. But unless it's a negative cycle, in the case of a negative cycle, the longest path does exist, but you need other algorithms to find it, not this one. Like, there are other algorithms to find, or you can just run, basically, if there's a negative cycle, this algorithm doesn't work anyway. Like, this algorithm, like, the important part is that this algorithm only works for positive weights. Yeah, basically the point is that anyway this algorithm only works for positive weights. Like, you can't use it for graphs where the weight is like -3 or -4 or something. This only works for graphs where the weight of every edge is a positive number. So it doesn't work for graphs where the weight of any edge is a negative number. For that you need a different algorithms, like Bellman-Ford and Lloyd-Warshall and everything. So yeah, I was planning to cover those also, but since time is less, so I can only cover this. Yeah, so um, basically, yeah, so this is the working of the Dijkstra algorithm. Let's now once jump to the implementation. um, where was that shortest route? So yes, okay. So basically, you want to, like, determine the length of the shortest route from city 1 to every other city. So yeah, and the important part here is that this is a directed graph. Like Dijkstra, it does not matter whether the graph is directed or undirected. For BFS, it only worked for undirected graphs, but Dijkstra works for everything. Um, yeah, so um, so this is a directed graph, so we'll only use and yeah, okay, one thing I forgot to mention is how do we represent weighted graphs in our code. So basically we use an adjacency list only, but along with the only the vertices that are adjacent to it, we also store the weight of that edge which connects that vertex to the other vertex. So for example, if 2 is connected to 4 with an edge of weight 3, then in the list of 2 you will have 3 comma 4. Basically, like, it is 4 comma 3. Basically, like, it is connected to vertex 4 with an edge with weight 3. So you won't only store the vertex that you are connected to by this edge, you will also store the weight of that edge. So yeah, it's only a simple extension. So UVW, and yeah, so now we will store both the weight and the vertex that we are connected to by this edge. And now for Dijkstra you need to use a priority queue, because a priority queue is a data structure which stores these pairs in sorted order, and it can give you the smallest pair in n log n time. Basically, you can find the vertex which has the shortest distance in log n time for every query, and since you only do this m times n plus m times, so it the total time complexity becomes n plus m times log n. Because once again the thing is, once you push a vertex into your queue, you know that it's going to be correct. Your answer is going to be correct. Like the extra, if you see the proof, like we don't have time right now, so we won't do that. But if you see the proof is based upon that principle only, that the weights are always correct. Like the first time, I mean the distances are always correct. So like the first time you set any distance to a particular value, any distance for any vertex, that is the last time you will, like once you pop it from your queue, that is the last time you are going to do that. Like it will never appear once again like, oh no, my maximum, like my best distance was 3 not 4. Like that's not going to happen. It's a proof by induction that it will never happen. So yeah, and that's where the no negative cycles part comes in. So yeah, you can read upon that if you want to. So basically m is some really large value, let's say 180, and there is a distance, and uh, and for this I will store the pair of long long and integer. Long long is the distance, and the integer is the vertex that that distance is for. And I will make a priority queue, and normally a priority queue gives you the greatest distance uh, on the front by default. But in order to but in Dijkstra we need the smallest distance. So in order to remedy this, you can use two solutions. One is to negate, one is to negate all the distances before putting them into the priority queue, so that when you get the greatest distance from the priority queue, you can again negate it again, and that will actually be the shortest distance in the positive world. The greatest distance in the negative world is the smallest distance in the positive world. And another thing is that the C++ gives you an option to uh, use this. You can use this syntax: pair long long comma int, greater pair long long comma int, comma vector pair long long comma int, pq, and this will give you a priority queue which has the greatest element, which has the smallest element at the front. Okay, so now let's quickly finish this. Everything is initialized to m initially, and while not period, and we will first push 0 comma 0 into our priority queue. And yeah, basically for all of your um, yeah, 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 if your current distance is more than the new distance that you would have apparently. And yeah, this is also an important part. Distance comma v is pq dot friend. If your distance does not match with your expected distance. Like what this means is that you found a better distance sometime after pushing this distance into your priority queue. Basically, this distance is an outdated one, so you should not be using it now, because anyway you have found a better distance later on. So what is the point of using this? So you won't be using this distance for your calculation, you'll just continue, because you anyway have a better distance later on. Like your distance, your d of v value can only decrease, it can never increase. If it is not equal, that means you have found a better d of v value from after that compared to before. So yeah, if d of u so you should continue, like you shouldn't update the remaining vertices. And now d of u is distance plus w, and pq dot push d of u comma u. And now I just do if d of n minus 1 is okay. Do we also need to print the path? No, we okay, we just need to. Okay. And everything is okay. And yeah, also this graph is directed, so we don't need to do it both ways, we can do it just one way. uh, and yeah, you can assume that it is possible. Okay, so we don't even need to handle that case. uh, plus uh, we will space, and okay, fine. And yeah. Because like see, like the point is that the what is the only time when you are changing d of u? The only time that you are changing d of u is when d of u is greater than distance plus w, and in that case you are updating it to distance plus w. So the only time it changes, it will decrease. So every time it changes, it will decrease, right? Like there is only one place in our code where we change the value of d of u, nowhere else we change it. And that also decreases it only. So yeah, okay. And let's submit. Boolean sky. uh, what it did I do something wrong? Wait a second. Okay, okay, right, okay. Sorry, I messed up a little bit. I haven't done this in a long time. So yeah, it's uh, vector and then it's greater. So yeah, make sure to remember this. Like it's pair long long command, then vector pair long long command, and then it's greater pair long long command. And this gives you a priority queue which holds the first element as the lowest one. Normally the priority queue holds the first element as the highest one, not the lowest one. But if you want a priority queue to hold the first element as the lowest one, then you can use this syntax. Okay, hopefully it is correct. Yeah, I swapped the vector and greater at first because uh, wait, what? Okay, wait, what did I do? Okay, oh my god, okay. I yeah. What did I do wrong here? Okay, give up top. Yeah, this is a priority queue. So what did we do wrong? Wait. Did I do something? Wait. Yeah, I just made a mistake. Uh, and yeah, no match for this. Okay, fine. Make pair of d of e comma e. Okay. Yeah, ignore my um, the mistakes and just wait a second. Fine. What happened here? Wait, what? Did I do something wrong? Oh, wait, okay. Did I do something wrong? It is sec. Oh, wait, okay. Oh my god, okay. How many stupid mistakes will I make? Okay, this is M, and yeah. Oh my god. Okay. Yeah, okay. Um, yeah, so I made too many stupid mistakes. Yeah, so anyway, just make sure to remember that you can use this to um, an extra constant c to every element to make it positive is wrong because like that will change your path length. For example, if you have a if you cross two edges in actuality, right, and let's say you added 10,000 to every edge to make it positive, so you don't know whether and let's say your shortest path from 1 to 7 came out to be let's say 30,000. So you don't know whether you crossed through two edges to make it 30,000, or whether you crossed through one edge to make it 30,000, or whether you crossed through three edges, because in three edges the offset will be minus 3 into 10,000. So your original weights sum would have been like your original distance in that case would have been 30,000 minus 3 into 10,000, which is 0. In the case of two edges, your original distance would have been 30,000 minus 2 into 10,000, which is 10,000. So like there is no way to track how many edges in the original graph were covered uh, in this case. Like basically in order to add an extra constant c to every element, in order when you add an extra constant c to every element, you need to know the number of edges in your current path in order to like only knowing the number of like the distance of the current path is not enough. You also need to know the number of edges in the current path, because the weight of the original path in the original graph, that the one that was there before adding an extra constant c, in that graph to get the same weight you need to subtract c times the number of edges in that path, and you don't know the number of edges in that path. It could be anything. Yeah, you can, but the point is that for example, like the metric you are optimizing is wrong. Like for example, let's say I got some path with weight 30,000 and number of edges in it is 2. So my original graph, and I kept track of it that it is 2. But let's say there was some path with weight 40,000 but the number of edges in that is 5. So I will never find that by Dijkstra because in my modified graph, and but in the original graph its weight sum would have been minus 10,000, while in this graph the 30,000 and 2 one, that weight would be 10,000. 30,000 minus 2 into 10,000, that is 10,000. But the 40,000 thing, even though in this graph it is worse than the 30,000 thing, in the original graph it would be better. It would have a sum of minus 10,000. So the thing is, like the metric you are optimizing is wrong. Like the number of edges of yours is not same. So if you are asked to find the shortest path with k edges or something like that, then you could think about this as a possible approach. Even then it's kind of hard to ensure that you will have exactly k edges because Dijkstra is not built for that. But in this case you can't assume, because like let's say you have um, let's say you have wait a second, let me just explain here. So let's say this is your original graph. uh, um, it's minus 10,000, minus 10,000, minus 10,000. So what's the shortest distance between this and this vertex? It's minus 20,000, right? Like, okay, it's a negative cycle, so anyway it's not defined, but let's say you had like, I don't know, 40,000 here, and let's say this is minus 10,000 and this is minus 10,000. So what is the shortest distance from this vertex to this vertex? It's going to be minus 20,000, right? Now let's say you added the constant, um, let's say you added the constant 60,000, or like let's say 100,000 to everything. So this is 90,000, this is 90,000, and this is 140,000, right? So now this is going to be your shortest path for this graph, right? So you will say, okay, so I have 140,000 shortest path, and minus 100,000 because it includes only one edge. But in this case you are missing this path which is containing two edges, which has cost 180,000, but since it is containing two edges, the actual cost of that path in this graph would be less than the cost of this path in this graph. So do you get what I mean? Like, this metric is flawed. Yeah. Okay. So does anyone have any questions about the Dijkstra implementation? And I will also share all of this in the server as well. So uh, yeah, if no one has any questions, I guess we can now end the lecture. Yeah. Um, okay. So I guess no one has any questions. So yeah, thank you all for listening, and yeah. Uh, okay. Thank you all for listening, and yeah, I hope you enjoyed the class. Yeah.